I want to talk about the upper and lower bounds for the solution set of this logarithmic equation. And I just want to do a rough sketch of an unshifted logarithmic function. Now it's always going to cross at 1, 0, right? We know that because it's the inverse of some exponential function that passes through the point 0, 1. Logarithmic function therefore has to pass through 1, 0. And it's a pretty slow growing function, looks something like this. Flattens out pretty quickly. Now, one thing we can observe is that the domain of this logarithmic function is 0 to infinity, right? And any unshifted logarithmic function has a domain 0 to infinity. And again, you can think of this as just about the line y equals x. It's just the inverse of some exponential function, okay? So, but in any event, so we know that just this piece right here would tell us the solution domain has to be have a lower bound of 0. So we know that 0 is less than x for sure, just because this term is in the equation. Now, right here, note that this number can't be any bigger than 788. So meaning you can't, let me just write this down. You can't exceed the number 788. Otherwise, you would have, say for example, 789. That would make this negative, okay? And that would make this entire input negative, which is not a valid input for a logarithm function. So we know that whatever the solution we obtain for this equation has to be trapped below by 0 and above by 788. Okay, now the rest of it is fairly straightforward. What we do, I took this term to the other side, and that's motivated by the fact that the log, just any log, the log of a minus b, this can be proved very quickly just from the laws of exponents. So the log of the difference is equal to the log of the quotient. And if you just think about the corresponding rule for exponential division, you can see where the minus sign comes from. Okay, so this is equal to the log of a over b. Okay, very well-known result. And again, it's easy to derive from the corresponding result for exponential functions. And so that's why I brought this over like this. Okay, and now we can use this rule. If you have the difference of two logs, that's equal to the quotient of the log, right? So we get this statement right here. Now notice x is greater than 0. We know that x is greater than 0, so it's okay to invert this fraction and multiply whereby the x's will cancel when you see that happening on this next line, right, folks? This is just basic arithmetic here. If you divide by a fraction, that's the same as inverting and multiplying. The x's would cancel because remember, we know x cannot be equal to 0, so we don't have to worry about that. Okay. All right, now the very last step on this one is going to be to convert this to the corresponding exponential equation. So every logarithmic statement corresponds to an exponential equation. So if we elevate, or if we do 14 raised to both sides, okay, meaning 14 raised to this quantity equals 14 raised to this quantity, we get this. And again, these two statements are absolutely equivalent. Okay? This exponential statement defines this logarithmic statement and conversely. Okay? And so what does that give us? That gives us 788. Oh no, folks, I got to do 14 squared. 14 squared is 196. So 788 minus 196 equals to x. And folks, that looks like 592. So x is equal to 592. And of course, the 592 falls within this. Let me go up further here. So right here, 592 would be in this interval that we determined was the upper and lower bounds for the solution set. So x equals 592 satisfies that condition. And x equals 592 is our final answer. Hope you enjoyed.